In this video, we're going to derive the formula used to calculate the total differential. The total differential is also sometimes just called the differential, dz. The formula used to calculate dz can be written in f with the subscript notation representing the first partial with respect to x and first partial with respect to y. These partials are calculated at an initial domain element and then multiplied by a small change in x or a small change in y. And then, of course, we have the del notation or the curly d notation that can also represent those first partials. Now in the derivation, we're going to look at a graph, and in that graph, we're going to see the values delta x, delta y, delta z, and those are going to be the changes in x, y, and z on the surface, and our dx, dy, dz values are going to be small changes in x, y, and z on the tangent plane. We'll see on the graph that the change in x on the plane and on the surface are the same, the change in y on the plane and on the surface are the same, but the change in z on the tangent plane is something that can be used to approximate the change in z on the surface. So let's consider the graph of some arbitrary surface, f at x, y, and a tangent plane that is tangent to that surface at the ordered triple, where the domain element is x, y, and if we're in the floor, we have a z value of 0, but that flies up to be a point on the surface, where the ordered triple would be x, y is the domain element, and the z value would be that domain element plugged into the surface function. Now let's move away from this domain element, a change in the direction of y and a change in the direction of x. So that we're now at a domain element back here where the x value has been altered by a small change in x and the y value has been altered by a small change in y. And again, since we're in the floor, the z coordinate is 0. And what we're going to do is we're going to fly this new domain element back here up and see where it intersects the surface, but also see where it intersects that tangent plane. So the ordered triple at which we intersect the surface is going to be x plus delta x, y plus delta y, and then the surface function evaluated at those two domain elements. Now, the tangent plane can also be called the linearization of our surface at this particular point. So let's use cap L to represent the function for the tangent plane, also known as the linearization of that function. So when we plug this domain element into that linearization function, what we get is x plus delta x, y plus delta y, and then the z coordinate is going to be that linearization function evaluated at these two domain elements. Now let's consider the change in these z value outputs. This first z value is the surface function evaluated at the original domain element xy. And at this elevation, we've applied those small changes in the direction of x and y to see what the surface value is at that domain element. And at this elevation, we're looking at the output on the tangent plane, which is also called the linearization. Now back up here, let's recall that these deltas are representing the change in x, y, and z on the surface, and dx, dy, dz are the small changes in x, y, and z on the tangent plane. And as well, recall that the changes in the direction of x on the surface and the tangent plane are the same. The changes in the direction in y on the surface and the tangent plane are the same. So let's try to understand that on our concept drawing. So let's look at the change in the direction of y. So when we moved in this direction and got to this point flies up through the surface and gets to the tangent plane, and we are using the same y value to determine that point. So the change in the direction of y on the surface is the same as the change in the direction of y on the tangent plane. And similarly, when the domain element moves in the direction of x, we get to this point here that flies up through the surface and then to the tangent plane at the same x coordinate, so the change in the direction of x on the surface and on the tangent plane are the same. Now what's different is the change in the direction of z. To get from the ordered triple that's generated from the initial domain element to the ordered triple that's initiated from this domain element, we first have a z value that starts here, and we get to a z value here on the surface, but a z value here on the tangent plane. So this is the change in z on the surface, but this is the change in z on the tangent plane. Now when dx and dy are very small, the total differential dz can be an approximation for delta z. So now we're looking for a formula for calculating this differential we're calling the total differential. So let's recall the meaning of our first partials with respect to x and with respect to y. If we were to slice the surface with a constant y plane, we would get an intersection curve, and the line tangent to that curve has a slope that's equal to this first partial with respect to x. Similarly, if we were to slice the surface with a constant x-plane, we get an intersection curve, and the slope of a line that is tangent to that curve would be the first partial with respect to y. So let's come down here to our concept drawing and think about slicing with this plane that is a constant x-plane. We get an intersection curve in here, and this line is the line that is tangent to that intersection curve when we slice with that constant x-plane. So the slope of this line can be considered that first partial with respect to y, but we can also think about it as rise over run, where the run is a small change in y, let's call it dy, and the rise is a small change in z. Let's call that small change in z due to that change in y. So while the slope of that tangent line is the first partial of f with respect to y, that's true, but it can also be considered a small change in z due to that change in y divided by the change in y. Considering it from two perspectives, number one, the partial perspective, and number two, simply rise over run. Now let's do something similar when we slice with this constant y-plane here. When we slice with the constant y-plane, we're going to get an intersection curve, and this line is going to be tangent to that intersection curve at that point. Now for the sake of our concept drawing, that line is also going to have the same slope as this line here because those two constant y-planes are parallel. And it'll be a little easier to illustrate what's going on over here on this side. So the slope of this tangent line is the first partial of f with respect to x, slicing with a constant y-plane. But we can also think about it as rise over run, where the run distance is dx and the rise distance is dz. Let's call this a small change in z due to a change in x. And the slope of this tangent line can be considered both the partial of f with respect to x, but it can also be considered rise over run, that small change in z due to the change in x, divided by that change in x. So let's multiply both sides of this equation by dy and multiply both sides of this equation by dx to get partial with respect to y times dy is that change in z due to the change in y, and over here we'll have partial with respect to x times dx is that small change in z due to the small change in x. Now to get the total differential, what we see is that we can add together this small change in z due to a change in y and the small change in z due to a change in x. These two quantities together is going to give me that total differential. So the total differential, dz, is going to be the small change in z due to a change in y, which is partial f with respect to y times dy, plus small change in z due to a change in x, which is partial f with respect to x, dx. And this is the formula for the total differential that we were trying to derive.